start a new topic. Today we talk about dynamic programming. Dynamic programming is a very important topic. It's one of the basic techniques used in algorithm theory. It's not like it's not an algorithm. It's not a data structure. It's like a common technique, and this technique is used in various different algorithms and alone to solve various different problems. So today we learn very basics of these techniques. We learn very simple problems, some very simple cases, and we will spend a few more lectures, like 3 or 4, even 4 lectures, when we will discuss some more complicated stuff. Today we'll discuss some very basics of the dynamic programming. Okay, let's start from very simple problem. First, let's try to calculate the Fibonacci numbers. So imagine you want to calculate the Fibonacci number. What is the Fibonacci number? Fibonacci numbers are defined like this. We have the first and second Fibonacci numbers equal to 1. And each next Fibonacci number is the sum of 2 previous Fibonacci numbers. Fn is sum of n minus 1 and Fn minus 2. 2. That's 2. Very simple. So, what happens if you want to calculate these Fibonacci numbers using this simple recursive algorithm? Like you make a recursive function, which works like this, like using this definition, like if n is less or equal than 2, then return 1, else return f of n minus 1 plus f of n minus 2. So, what will happen if you try to run program like this? It will calculate the Fibonacci number. No, that's correct. This is absolutely correct program. If you run it for number n, it will return the nth Fibonacci number, as expected. But the problem is that time complexity of this program is too big, because if you try to calculate time complexity, again, how we can calculate the time complexity for recursive functions? We calculate it like this. So what is time complexity for number n? So if we run this program, this parameter n, it will make some constant number of operations here, plus 2 recursive calls. So this recursive call will cost you t of n minus 1, and this recursive call will cost you t of n minus 2. Okay, so this exactly like we did in the first lecture. Yes, this is mostly like the master theorem, but not exactly, because here we have different arguments. Here we have n minus 1, here we have n minus 2. But it's not a big deal. So it's basically the same as we did on the very first lecture, when we discussed the time complexity of the recursive procedures. Now, what is time complexity here? Well, it's easy to see that this number is growing basically the same as the Fibonacci numbers themselves. So t of n is like greater or equal than f of n. We also have plus 1, but it makes this even bigger. Yeah? So it's not less than these Fibonacci numbers. And Fibonacci numbers then grows exponentially. So this is greater or equal than some, let's say, phi in power n. For some positive constant number, for some phi. You can calculate this number phi. It's not that. Maybe you know how the Fibonacci numbers grows, but it's not the topic of this lecture. The important part is this numbers grows exponentially. So this algorithm has exponential time complexity, and that's bad. We don't want some algorithms to have exponential time complexity. So how can we fix this? Let's put what's happening when we run this recursive function. For example, if we run recursive function f with parameter, let's say 10. What's happening? We started this recursive call. Now we make two recursive calls. First recursive call is with parameter 9 and second with parameter 8. And each of these two recursive calls make another two recursive calls. So we have here two recursive calls with f of 8 and f of 7. And here we have f of 7 and f of 6 and so on. Now let's look what we can improve here. Let's look on the following. Let's look on this recursive call, for example, and this recursive call. These two recursive calls calculate the same value twice. So here, all this we do to calculate the 8th Fibonacci number, and then we go back here, we calculate the same number again. So these two recursive calls calculate the same Fibonacci number twice. So basically, we calculate the 8th Fibonacci number not once, but twice. But twice is not big. Twice is not a big deal. So the worst thing happened when we go to the next number. For example, for the 7th number, we calculated here. Here we calculate f of 7. Here we calculate f of 7 again. And here we calculate f of 7 the third time. So 7th Fibonacci number is calculated 3 times. It's calculated here, here, and here again. And the next Fibonacci, if you try to calculate number of times you calculate the 6th Fibonacci number, it's calculated 5 times. It's calculated here, 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 and here. So each next Fibonacci number is calculated much more times than the previous Fibonacci number. Let's try to fix this. Let's try to calculate each Fibonacci number only once. How can we do this? We'll use the basic technique which calls memorization. We will save the results of this function for each number n. And if we already calculated this number before, we will just use this memorized answer and return it immediately. So let's improve this. Let's say something like this. We will use some array which stores all the calculated values. So if value is already calculated, so if we have result for this n already stored in this array, so if this, let's say if we have result for this n already calculated, let's say not equal to it means that we already calculated this Fibonacci number. We can just return this number. And if not, then we do the same as we do here. So we see if n is less or equal to 2, then the Fibonacci number is 1. Yes, it will be sum of f of n minus 1 plus f of n minus 2. Again, it's the same as here. Just use the same code from this function. And in the end, just return this result. Nice. That's all the improvement. Again, what we did. Here, instead of just getting this number, we put this number in the array. So here, we use this array to store all the previously calculated Fibonacci numbers. And here we use these pre-calculated numbers to do not calculate them twice. So if we already calculated this value before, then we just take this number from the array and return it immediately. That's all. Yes, here we actually use an additional array of size n. Yes, so we need additional memory. Yes, if we want to calculate the 100 Fibonacci number, we need to have an array of size 100. We will not improve this today, but you can think about how to improve this. That's not today's topic. You can actually get rid of this array, but not today. Here. So now what we wanted is to improve the time complexity, because time complexity of this function is exponential, and we want to find a way to improve this. So we want to improve the time complexity, not the memory complexity. Okay. So what is the time complexity of this new improved recursive function? Let's see. Each time when we enter this function, we do one of two things. If the result is already calculated, then we spend constant time here. So we spend constant time. We just go into this array, take this result, and return. That's all. And if result is not calculated, wasn't calculated before, then we need to do all this stuff. But we do all this stuff only once for each value n. So this code is executed exactly once for each value of n. So total time complexity will be linear, because this code is only executed once for each different value of n. So we have n different values, so we can execute this code only once. So the total time complexity of all these recursive calls will be linear. Let's look what's happening with this recursion tree. So what's happening here? When we go to the left branch, then we go back, go to this branch, this f of 7 is already calculated here. So in this branch, we don't go deeper. So we stop here and immediately go back. And the same thing goes here. So when we try to calculate this 8th Fibonacci number for the second time, we already calculated it here. So here we just go in this section and return this result, which we calculate here. So here we don't do this again. And so on. So the tree of recursion will look like this. So we only have the left branch, and right branch is always like this. For 6. And so on and so on. So it looks kind of like this. It will look like this. And the total number of elements is linear. So we have n elements here plus n elements here, so 2n elements. So total number of recursive calls will be like 2n. Oh, it's t of n equal to. So the time we need to spend for this number n is linear from the number n. Okay, that's all. Now, this program is a little bit overcomplicated. We can do the same thing without any recursion. If you think about it, what are we doing here? Here, we go deep into this recursion, and now when we go back from the recursion, we calculate the Fibonacci number. So when we get from the recursion, we take these two numbers, calculated into recursive calls, add them to each other, and put the result in this position. So each time we come back from the recursion, we sum these two numbers and calculate the next Fibonacci numbers. We can do the same using basic for cycle. Let's make improved procedure here. What can we do? We can just assign first two values to 1, and then make a simple for cycle, for loop. It's called loop. English is different. For all I from 3 to n, we just take two previous numbers, sum them, and put here. equal to res of I minus 1 plus res of I minus 2. That's the whole code we need. So what we're doing in this code, we just create this array of pre-calculated values for each Fibonacci number. And then calculate these Fibonacci numbers one by one. So each time we try to calculate the if Fibonacci number, we already calculated two previous Fibonacci numbers. So we take sum of two previous Fibonacci numbers and put them in this cell. And we're going one by one. After we reach the last cell of the array, we will find the nth Fibonacci number. That's what we try to achieve. That's all. And this time complexity is obviously linear as well, because we have only one loop, so we have n iterations here, so it's obviously big O of n. By the way, you can calculate Fibonacci numbers even faster. If you're interested in Fibonacci numbers, they can be calculated fast because Fibonacci numbers are actually well researched. So there are different techniques to calculate Fibonacci numbers without stuff like this. But that's not the topic of today's lecture. Now we learned how to calculate the Fibonacci numbers. That's kind of interesting for somebody, but not very practical. So in practice, it's strange. Why do you need to calculate Fibonacci numbers? It looks like not very real topic. The interesting part that you can use the same technique to solve some algorithmic problems which are much more close to real life. We will not have real life problems today. We'll learn only the very simplified problems, but the problems like these we will have the similar problems a little bit more complicated later in this course. So today we have very simple problem, very simplified, specifically to learn some basics. For example, let's solve problem like this. Well, problem. Let's have an array. Let's have some strip of some squares, and so these squares are numbered from 0, let's say, to n minus 1. Let's say minus 1. Yeah, it's not important, but and there is a small grasshopper living on the leftmost cell in this array. So here we have looks fine. I'm not sure why it's grasshopper. It's some classical problem in Russian programming school. I'm not sure where it's come from, but the first classical problem of dynamic programming was about grasshopper, so it's kind of Russian tradition to learn dynamic programming. So there is a small grasshopper living on the leftmost cell of this array, and he wants to get to the rightmost cell of this array. So he wants to move from this cell to this cell, and he can make jumps. And he only makes jumps to the next cell and to the cell after it. So if he's standing in cell I, he can make jump to cell I plus 1 and to cell I plus 2. There are two types of jumps. There are small jump and big jump. Oh, yes, there's a frog in educational content. That's fine. I don't know. In Russian tradition, there always was a grasshopper. I don't know why. That's the way I learned the dynamic programming. The way I think the people before me learned it. I know where it's come from. Now, we want to move from here to here using these jumps. For example, let's see. There are too many cells. For example, we can make jumps like here. We're going to start from 0, move to 2, then to 3, then to 4, then to 6, 8. So that's one of the possible ways to get from cell 0 to cell 9. That's not the only way. There are many different ways to get from this cell to this cell. For example, we can take another path. So we can start here. Well, let's say we can jump to cell 1, then to cell 3, then to cell 5, then to cell 6. That's another possible path. So there is one possible path, another possible. There are many different ways to get from first cell to the last cell. So the problem is to calculate the number of different paths from the first cell of the array to the last cell of the array. To express. Okay. How can we calculate this number? Let's see. Imagine you want to calculate the number of ways to get to the last cell. So we have this last cell with index 9, and we want some path which ends in the cell 9. So if we end in the cell 9, let's look, what was the last jump before we reach the cell 9? We can make the last jump either from the cell 8, so the last jump may be from cell 8, like this. That's the case 1. Or we can reach the cell 9 from cell 7, so we can have something like this. Now, let's calculate number of paths like this and number of paths like this. How to calculate number of paths like this? So what's happening? We start from cell 0 and we make some jumps. And we end in the cell 8. And then we make the last jump to the cell 9. And here we do basically the same. We start from cell 0, then make some jumps. And we end in the cell 7. So if we want to end in the cell 9, we need to get sum of these two numbers. We need to get the number of paths to the cell 8 and number of paths to the cell 7. So first number will be number of paths like this, and the second number will be number of paths like this. If we have, let's say, d of n is numbers of paths to cell n, we can calculate it like this. We can take the number of paths like this. These are the cells. Again, these paths are the cells which have the previous cell is the cell n-1. So we need to get from cell 0 to cell n-1 and make plus one step here. It will be number of paths like this will be d of n-1. And number of paths like this will be d of n-2. And if you look here, you have the same formula as we used in Fibonacci numbers. So we can calculate these numbers using the same technique we used when we calculated the Fibonacci numbers. Just the same technique. Should I write the code? Let's write the code so it will be simple. How to write the code? We calculate the first values like here. We calculate the first values just by hand. So let's say d of 0 will be 1. Okay, let's do it in a simple way. And d of 1 equal to 1. And now we iterate over all values from 0, 1. We have from 2 to n minus 1. And use this formula to calculate the next value of d. This is d of I equal d of I minus 1 plus d of n minus 2. That's the whole program. Okay. Again, let's make an example. So let's start here. So what we're doing, we make this array D and calculate the number of ways to get to the cell number n. And we calculate it from left to right. So first we calculate these two numbers, so we have only one way to get here, only one way to get here. Now, for this cell, there are two possible ways to get to this cell. For this cell, there are three possible ways, because one way is to reach cell 1 and then jump here, and there are two ways to get to cell 2 and then jump from 2 to 3. So we have three different ways to go here. And so on. So here we have 5, 8, 13, and so on. Cool. Yeah. Can we say that there are only values better because there's a lot of it? Yes, that's exactly what we're doing. There are only two ways to get to the cell 9, from cell 8 and from cell 7. So if we want to calculate the number of paths like this, we need to calculate number of ways to get to cell 8. This is in this cell library. If we want to get from here, there are d of n minus 2 ways. That's the same as you said. Cool. Again, this problem looks kind of not very natural. Like it's kind of strange. You want to calculate number of ways to get from one point to another. There are situations when there are some strange situations when you need to calculate number of ways to get from point to another, but it's not usually what happened in real life. What may happen in real life, situations like this, is when you need to calculate the number of some combinatorial objects. For example, let's say you have Boolean vectors of size n. So it's vector of ones and zeros. And in this vector, you don't allow to have two ones in the neighboring positions. So there is no two ones next to each other. For example, we may have something like 0, 1, 0, 0, 1, 0, 1, like this. And you want to calculate a number of different vectors like this. How you can calculate this using the same technique? Let's see. We have this vector. Let's look, for example, on the rightmost position. So what's happening in this last cell of this vector? There are two variants. We may have 1 or we may have 0. If we have 0 in the last position, then here in the first n-1 positions, we may have any combination of ones and zeros without two ones next to each other. So here we have n-1 elements, and we can put any combination of ones and zeros which satisfy this rule. So what is the number of these combinations? Well, these combinations is this is the same problem, but for n-1. If we have this d of n is the number of different vectors for n, then if the last element is 0, the number of such vector is d of n-1. Minus 1. And if the last element is 1, then what's happening? If last element is 1, then the previous element should be 0, because we cannot put two ones next to each other. So this element is 1, this element is 0. And these elements may have any combination, again, any combination of ones and zeros without two ones next to each other. So here we have n-1 minus 2 elements, and we can put any valid combination of ones and zeros. So number of combinations like this is d of n-2. That's all. Now all we need is to get sum of these two combinations. So all vectors of size n can be split into two separate sets. Vectors with last element equal to 0 and vectors with last element equal to 1. And there are d of n-1 vectors like this and d of n-2 vectors like this. So to calculate number of vectors of size n, we just have the sum of these two, and that will result. And again, we have the same formula as we used here. So each next element is just sum of two previous elements of the array D. So we use the same code to calculate the same values here. Maybe different starting values. Yes, it will be d of 0 will be equal to 1 and d of 1 will be equal to 2, because there are two variants for one element. Cool. That's all. This also looks not very natural. It's kind of strange. You want to calculate the number of different combinatorial objects. This may happen at some point, for example, if you're using some, for example, in some coding theory, if you have some message and you want to encode this message using vectors like this. So there is some strange channel which allows you only to use vectors like this to transmit your message. And you want to calculate the amount of information you can store in one message like this. So the amount of information you can store in this is the logarithm of the number of different combinations. So calculate number of combinations, get logarithm of this. It will be the number of bits you can store in this one message. Something like that. So it's kind of more practical, but not exactly. Let's go back here for a little. I want to show you some more problems. Let's change something a little bit, just to play with it a little bit more. What will be changed if we have some strong grasshopper and he can jump to cells I plus 1, I plus 2, and also I plus 3? So he went to the gym, so his muscles are more stronger now, so he can jump to the cell I plus 3. What will be changed in our program? Not very much, actually. There will be the third case. Before we had only two cases. We can get from cell I minus 1 and I minus 2. And now we had the third case. We can get to cell n from the cell n minus 3. So we need to add another 7 here. So here will be also plus d of I minus 3. And now we need to actually, in this code is not good. because here, if we start from cell 2, we need to access cell I minus 3. So we need to access cell minus 1. It's not good. So we need to add another. So we need to start from cell 3 and calculate first 3 cells by hand. And for the second cell, the number of ways will be 2. So it's it started to became a little bit more complicated. Here we have 3 values calculated by hand, and we have cycle starts from 3. And if n is less than 3, we have some special cases. Too many special cases is always bad. And if you extend it a little bit more, so if you allow the grasshopper to jump, let's say, k cells, so he can jump to the cell I plus 1, I plus 2, plus 3, and so on to the cell I plus k. Then it becomes a little bit more complicated, so you need to calculate the first k cells by hand, and you don't know the value of k. Situations like this usually can be optimized like this. Let's calculate only the first value by hand and make the cycle from the second one. Let's get rid of this. So what we need to do here? We need to calculate the sum of k previous values, right? Oh, I already raised this. I start from cell 3 because I use 3 previous values. So do not have the integer overflow, do not have array out of bounds exception. So when I go to cell from cell 2, if I go to cell 2 minus 3, I go to cell minus 1. I don't have cell minus 1. Yeah. We'll improve it right now. So how to improve this? We will make a cycle or a loop. It's called loop in English. It's different language. Okay. Make a loop for j from 1 to k. And this will be the length of the last jump. So we have cell I and we jumped from cell I minus j. And this last jump have the length k. And now here I will make an if statement. So if I minus j is greater or equal to 0, then I have this cell. So this is the possible jump. And I just add this value to my value. That's all. That's the whole program. That's how you calculate the number of ways to get to the last cell. If you can make jumps to 1, 2, and so on to k. If the maximal length of the jump is k. No. Actually, this program is quadratic time complexity. Here we spent n multiplied by k time complexity. You can easily improve it to be linear. Any ideas how to do this? Any ideas? Any ideas? Any ideas? Any ideas? Here I have 2 loops. I have first loop iterating over the cells, and the second loop I use this loop to calculate the sum of of previous values. So when I calculate this element, I need sum of k previous values. I need to get sum from I minus k to I minus 1. So I need to calculate this sum. So it's easy way to calculate the sum on a segment in array. Just calculate the prefix sums. So when you need to calculate this sum, you get this prefix sum minus this prefix sum, and you get the sum on this segment. So we can get rid of this second loop, and here you just get this prefix sum minus this prefix sum and get the sum on the segment. If you do this, time complexity will be linear. Yeah. Good. actually spent almost an hour of this. Good. Now, let's go next. Okay, this all problems we discussed by now was about calculating the number of something. We calculated number of such some paths. We calculate number of some combinatorial objects, something like this. These are one of the types of the dynamic programming. So sometimes dynamic programming used to calculate the number of something, number of some strange objects. In practice, it's not very common. So in practice, like if you're writing some real project, you don't usually want to calculate the number of something. Sometimes you need to do this, but not usually. The more common application of dynamic programming is when you need to optimize something. So you have some optimization problem. Let's write something. Let's make some optimization problem. Let's have our grasshopper again. It jumps to 1 or 2 cells forward, like the first problem we had. And now we need to pay for each cell we visited. So we start from the first cell, we end here, and for each cell we visited, we pay some amount of money. So we have, well, let's see, here we have 3, 1, 2, 6, 7, 1, 5, 4, 3. Let's see, these 2 cells will be free. So each cell have some cost. If we jump on this cell, we pay this cost to somebody. I don't know, the strange who owns the cells of this, right? I don't know. Maybe some other grasshoppers. I don't know. What's happening in the insects world? I don't know. Did you watch The Bug's Life? It's, I think some big grasshoppers. No, grasshoppers was bad. Yeah, so there were ants and grasshoppers. Yes, yeah. Not today. So what happens? You want to calculate you want to find the path from here to here, and to spend the minimal possible amount of money. Now this looks like something very important practical problem. So in various different problems in real life, you want to calculate something which costs you the minimal possible amount of money. So there are some other problems when you need to optimize something. You want to find best objects of all possible objects. Stuff like this. Well, so how can we do this using dynamic programming? We can do it in the same way we did calculate this number of paths in the previous problem. So again, let's split all the possible paths to 2 different sets. So if we want to reach the cell, the last n cell, then the last jump was from the cell n-1 or from the cell n-2. Now, what happened when we need to calculate optimal paths from this group? Optimal path in this group is composed like this. We start from the cell 0, then we make some jumps, we reach the cell n-1, and then make one more jump to cell n. So if we want to calculate the minimal sum on this path, we want to find the optimal path from cell to cell n-1, and then make one more jump to cell n. So optimal path here, let's see here. Can I erase this? Yeah. I'll use the same array. So if we say that d of n is the minimal cost we want to pay to reach the cell n, then in this case, we need to reach the cell n minus 1 with minimal possible cost, plus make this one jump. So the minimal cost here will be d of n minus 1 n minus 1 plus cost of cell n. In the same way in here, if we want to reach it from cell n minus 2, we need first to reach cell n minus 2 with minimal possible total cost, and then make this jump. Now, we need to find the optimal path. So we need to get optimal path from this group and optimal path from this group. And now take just minimum of these two. So this d of n will be minimum of these two options. So we either we go to cell n minus 1 plus this one jump, or we go to cell n minus 2 and then make one more jump. That's all. You can put this c of n out of this minimum, but it's good enough. I think it's more visual here. So again, what we're doing, we try to find the optimal path to cell n. There are two cases. We can go to cell n from cell n minus 1 or from cell n minus 2. In both cases, we want to optimize the path to the previous cell, because the sum is minimized when both elements are minimized. So that's basically because the sum is a good function. If you want to minimize the sum, you want to minimize both the summands of the sum. Cool. For example, in this case, so again, what we're doing, we create this array D. We create array D and go from left to right and calculate this array using this formula. Just go from left to right. Again, for the first cell will be 0, here will be 3. Now for each next cell, we take minimum of these two values. So for example, to this cell, we can go from cell 0 or from cell 1. Here the cost will be 2, here the cost will be 5. Take minimum of these two, so minimal cost will be 5. And so on. So here the minimal cost will be 3 plus 6 will be 9. Here minimal cost will be 5 plus 7 will be 12. Here minimal cost will be 10. Here the minimal cost will be minimum of 12 and 10 plus 5, it will be 15. Here it will be 14, it will be 14 plus 3, 17. Arithmetic is difficult. And here will be 14 plus 14. Should I write the code? Do you need the code? I think the code is pretty simple, but let me write it. I'm always writing the code. So the code is pretty simple. You just, again, if here I use two previous values, so I will calculate two first values by hand. So d of 0. Oh, now the board is wet. D of 0 is 0 and d of 1 equal to c of 1. Again, we will avoid with this situation later. Usually you don't want to initialize more than one initial state, but that's fine. And now we iterate for all values of n. We iterate for all I from 2 to 10 and calculate the of I d of I is, let me put this c of n out of this. So it's minimum of d of n minus 1 and d of n minus 2 plus c of not I, not n, not n, it's I. That should be I. That should be I, and that should be I minus 1 and I minus 2 plus c of I. Oh. Why is it wet? Did I spill something? No, that's fine. Looks fine. It looks fine. My bad. Here it should be not 5 but 2, right? So everything is wrong. Let's just change this as 5. Yeah, much better. That's the easiest fix. Yep. Cool. Now, what I was talking about. Okay, and again, let's update it again. What happened if you want to make jumps not to 1 and 2, but to all lengths from 1 to k? So if you're making jumps from cell I to all cells from e plus 1 to e plus k. So if you want to make jumps like this, how can we change our program? Quite easily. If you want to do this, you need to have minimum not of 2 previous values, but of k previous values. So when you get to cell I, you moved from one of these cells, from I minus k to I minus 1. So the previous cell was one of these cells. What you want to do is take minimum none of these 2 cells, but of k previous cells. Let's modify our program. What? I didn't answer. What? Who would store in the PS dpi from previous index, dpi from previous difference? I don't get your question, sorry. So you have 2-dimensional array. Why do you need 2-dimensional array? Sorry, I don't get it. We'll discuss it after the end of the lecture, okay? It's kind of complicated. There are different techniques to implement dynamic programming. Maybe your technique is also good. I just implement my technique, and if your technique is good also, we will discuss it after the end of the lecture. What we need to do? We need to get minimum not of 2 previous values, but of k previous values. Okay, let's make the second cycle. So how do you calculate minimum of k elements? You initialize minimum with plus infinity, and then each time you relax this minimum with the new value. So d of I equal to plus infinity. Let's start from 1. I'll remove this. Again, I only want to initialize the first element because it's much more comfortable to initialize only one element. And now we make the second loop from 1 to k. If we have this element, if I minus j is greater or equal to 0, then it's possible to jump from I minus j to I, So I update my minimum to d of I and d of I minus j plus c of I, like this. Yeah, you're fine. Again, this program runs in quadratic. Here again, we have time complexity and multiplied by k. It also can be improved to be linear. It's a little bit more complicated. You can't make prefix minimums because you cannot get minimum on a segment from two prefix minimums. So it's not like in prefix sums, but it can be done. So you need kind of sliding window and calculate the minimum in this sliding window. You can do it by using for example, by using Q with minimums, like we discussed when we discussed stacks and queues. You may have a queue and calculate minimum in this queue using Q based on two stacks. It was a long time ago, but maybe you remember. So you can make a queue, and you may know the current minimum in your queue when you make queue based on two stacks, for example. So if you do it like this, then you can calculate the minimum of k previous elements in constant time. So this can be improved to be linear, but I will not do it. Cool. Nice. No. This is not all, because my program only calculate the value of the optimal answer. So if you run this program, you will know that the optimal path if you want to go from cell 0 to cell n, you need to spend minimum 14 coins. That's a good result. So if someone came to you and said, I need to get from here to here with minimal possible cost, and you like to talk to him like, you can do it spending 14 coins. He said, thank you for information, but how? And you say, no, I don't know how, but somehow you can get the optimal path of 14 coins. I have no idea how you can do it, but it will cost you 14 coins. That's not exactly what you want usually. Usually you want to find the path itself. So how to calculate the path when you calculated these values? Pretty easy. Let's see. So we want to get here spending 14 coins. So how can we do it? Let's see. How did we get here spending 14 coins? No, we jumped from this cell to here. So we spent 14 coins to get here and then make this jump. So the last jump was this. Now, how did we get here spending 14 coins? No, we jumped from here to here, spent 10 coins here plus 4 coins here. So the previous jump was from this cell. And so on. How did we get here? We jumped from here. And how did we get here? We jumped from... That's too boring. Yeah, that's too boring. Okay. We always have jumps of length 2. That's not usually what happened. Nah, that's a boring example, but okay, that's fine. So again, we start from the last cell, and each time we try to get the previous cell in this path. How can we do it? We just find how did we get this value of d. So we get this value of d by adding this 14 and this 0. So the previous cell must be this. And we get here by adding this 10 and this 14. So the previous cell was here, and so on. So we jump from the end to the beginning and restore this path. Actually, if you want to implement this in practice, like in contests, so most of you came from Codeforce, so the much more easy way to do this is not to, because you need to do kind of the same thing twice. So you calculate this d, and then you make the same thing each time you take the minimum of these two values and so on. You can just save this value that you used when you calculate the minimum value of d. So instead of just restoring it by this array d, if you have enough memory, if you can make another array, you can create another array, and in this second array, calculate the previous element in the path. Create another array p, and this p will be previous cell on path to cell n. So we go from left to right and calculate two arrays in the same time. So again, we start from left to right. So we take, no, this will be so this will be, so for the first element there is no previous element. For this is 0. Now for this element we jump from here, so the value will be 5 and the previous element will be 0. Now for this element we jump from here, so the value will be 3 plus 6, it will be 9, and the previous will be this element, so 1. Here we jump from here, so it will be 12, previous one will be 2, and so on. Here it will be 10, it will be 1, 2, 0, 1, 2, 3, and so on. Here it will be 15, the previous one will be 5, right? And so on. So just maintain two arrays. First array calculate the optimal value, and the second array calculate the previous element to achieve this optimal value. So let's update our code a little bit. So what's happening here? We say that if the new variant is less than the previous element, so if this d of I minus j plus c of I is less than current element of I, then we update this minimum and save the previous element. We save the way how did we get this minimum. So we get this minimum of I by moving from cell I minus j. And now in the end we just move from the last cell to the first cell using these pointers. What about 2, 0, 2, 2, 0? Oh, if you have two same elements, we can move from either of them and we will get the same sum. So if we have two equal elements, so the minimum is one of them, we can move from any of them. Okay, so you will get the same result by moving from both results. So if you just want to find any, if there are several possible optimal answers, you will find one of them if you just follow one of these links. What was I talking about? No. So in the end, if you want to restore this path, you just start from the last vertex, from the last cell. It's not a graph. It's not a graph by now. Let's say x equal to n. And then use these links. Again, we start from the last cell and then use these links to restore the path. So this is the value of x, and then we move x to the previous element in the path. Well, we have 0. Let's put -1 here for simplicity. Like this. Yes, the path will be reversed, so we need to reverse the path. That's all. That's how you calculate the optimal answer. So we find the value of optimal answer, find the optimal sum. And then we use these links to find the path itself. So that's how it's done. Good. Good. I want to raise something. Have any more questions before I erase everything? Okay, let's move next. Now, today we'll cover only the basics of dynamic programming. We'll cover some more complicated topics in the next few lectures. We have like 3 or 4 lectures about dynamic programming. Now, you can do the same technique in various different problems, which looks kind of like this. For example, if you have, let's say you have a square table like this. And there is somebody who's, again, in the Russian tradition, it is a turtle here. I don't know why, but let's be the turtle. That's the turtle. So it's moving from here to here, and each time it moves to the right or down. So he tries to get from here to here in shortest path. So shortest path is n-1 plus m-1 steps. So you do something like this. So he can only move to the right or down. And again, let's say that in each cell of this array there is something. Let's say something good. What do totals like? Let's say we have some grass in each cell. We have some amount of very tasty grass. So he moves from here to here, and each step, when he steps on this cell, he can eat all the grass in this cell. Let's say we have different amount of grass. So like 3, 2, 3, 1, 6, 5, 7, 2, 3, 1, 2, 3, 2, 1, 6. So your task is to go from here to here, moving only right and down, and calculate the maximal possible sum. Yeah, it sounds something. Yeah. It's strange why you want to sum all the juiciness of the grass. Yeah, I don't know why. You just want to calculate the maximal possible sum of it. Now, how can you do this using dynamic programming? In the same way we did here. We will calculate the optimal way to reach each cell of this rectangle table. So for each cell, we'll calculate the optimal way to reach this cell. But here, this is a two-dimensional problem, so we will have a two-dimensional array. So we'll have Tij equal the maximal sum to reach cell Ij. And yeah, so how to calculate this? Exactly the same. So how it's working? you have some states of your dynamic programming. In our case, state is just the cell we want to get to. And for each state, you want to calculate how did you get to this state. So if you end up in the cell ij, what was the previous cell on your path? In our case, if we're moving only right and down, then the previous cell was one of these two cells. So we moved either from this cell, ij minus 1, or from this cell, this is I minus 1 and j. So the last step was from here or from here. And if you want to find the optimal path to this cell, you need to find the optimal path to here. So we have some path to here plus this move, or some path to here plus this move. Now we have optimal path from this, an optimal path like this. Take minimum or maximum of these two paths and calculate the result here. Okay, it's just the same idea, but we have two-dimensional cases and one-dimensional case. But the code will be the same, just we have two loops instead of one loop, because it's two-dimensional. But the idea is absolutely the same. You do just the same thing, but in this case. Basically, if you're familiar with graphs, you can do the same thing on any acyclic graph. So if you have a cyclic graph, and so you have some graph like this. We will talk about graph algorithms in the third semester. It will be in the year after. But if you just know how the graphs work, if you have some acyclic graph, you can do the same on this acyclic graph. Just you go in topological order and calculate the value for each vertex from left to right. It's just the same. Good. And the final problem I want to discuss today is the following. Let's add some more complications to the grasshopper problem. I don't want to clear this, so let's move back to the grasshopper. Let's add some more complications. Let's say the following. Let's say if we have some sequence of jumps, each next jump cannot be shorter than the previous jump. So if we jump on then let's say k, then the length of the next jump should be at least k. So the next jump should be at least k. Let's say we cannot break, so the brakes are broken, so he cannot stop immediately. If he gets some velocity, and let's solve all the previous problems. So we can calculate the number of ways to get from first cell to the last cell, or we can calculate the optimal path, something like this. So let's solve all the same problems, but with these complications. So each next jump should be not less than the previous jump. Yeah, it has some momentum, yeah. How to solve this? Again, what is the idea? Let's look on the current position of the grasshopper. There are two ways of thinking about this. First way of thinking about this is like this. Let's try to solve the problem. So we want to get here. So we want to get to the cell n. Let's look on the last jump. The last jump was from this cell, or from this cell, and minus k, and his left k. What was your question again? Sorry, I lost a question. Sorry. Can you ask it again? What's happening? So if we need to get to cell n, we look on the previous cell. So we jumped from cell n minus k. Now, what is the optimal path we need to find to cell n minus k? Now, what we need to find? We need to find the optimal path to cell n minus k, but not all these paths are exactly the same, because we need to get to this cell n minus k with the last jump less or equal than k. So this jump should be less or equal than k. So we kind of reduced our problem to the following problem. So when we need to reach the cell n, we reduce the problem when we need to reach the cell n minus k, but we have a restriction that the last jump should be no more than k. You may think about it like this. And now all your problems looks like this. So you need to get to some cell with the restriction that last jump should be no more than k. So you have two parameters of your problem. You have first parameter is the cell you need to reach, and the second parameter is the length of the last jump. If negative values, I think nothing changes if negative values. I believe in this realization nothing changes if I have negative values, because I have plus infinity here. No, I don't see any problems with negative values. The matrix problem. No, here I also don't see any problems with negative values. We will just some sums will be negative. Now you have maximum of these two values. You have maximum of two negative numbers. I believe I don't use non-negativity in this case. No, I think negative numbers are fine in all problems we discussed today. What I was talking about? Here. So your problem has two parameters: the cell you need to reach and the length of the last jump. Another way of thinking about this is like this. Let's try to someone describe the current state. So there is some process. Yes, there is some process. You need to get from this state to this state. So your system kinda have some states. That's a way of thinking about dynamic programming. And you want to describe your state in minimum number of variables. So which variables describe your current state? So your current state is where do you stand and what was the last jump you make. Yeah? So you have two parameters of your current state. What is your current cell and what was the last jump you made, because this jump restricts your next jump. Yeah. So these two variables just like fully describe your current state of your system. And in this system, you kind of need to get from initial state to the final state. Something like that. How it's working? If you kind of feel you need two parameters in your system, so you kind of you need to have two-dimensional array. So you need to describe all the states of your system, and for each state of your system, find the optimal answer. So what's happening, for example, in this problem? Let's do it like this. So let's say that d of n and k is the optimal answer. What's optimal? What we want to do? What we will calculate the optimal path or number of paths? What do you like? let's calculate the minimum cost. Minimum cost will be just to jump here. It's not fun. Let's calculate number of ways. To cell n with last jump what do you want to do, equal to k or less or equal to k? There are two ways. You can make last jump equal to k or less or equal to k. Let's make it less or equal to k. It actually will be fast in this way. Possible then. No, you don't want to, you want to make the number of states less as possible, because if you make the number of jumps in your current state, the number of states will be too big, and you want the number of states to be small. Number of states is state is something that describes what you can do in your system. So if you stand here and last jump was k, then you can make jumps starting from k, so from k to k plus 1 and so on. So these two numbers fully describes what you can do next in your system. That's how it's usually working. Because minimum cost is just jump from here to here. I don't restrict the length of jump. So the optimal path will be just to jump to the final cell. So it's not that fun. But if you have negative numbers here, it may be fun. But if all numbers are positive, it's kind of strange. Oh. Now, how to calculate this number? Again, let's look here. So this is just write it again. So we have cell n, and the last jump has length at most k. Let's iterate over all possible values of the last jump. So last jump has value less or equal to k. So is j is equal to k. So we have this cell n minus j, and this jump was less or equal to j. Right? So we have jump from here to here of length j. So we need to get to cell n minus j with the last jump at most j. Right? Let's do it like this. So we need to sum. I will not write the code, okay? So you can write the code, it's simple. We need to sum all the ways for all j from 1 to k. We need to find the number of ways to get to cell n minus j, with the last jump be no more than j. Oh, cool, square rating. Cool. No one ever rated me before. Hello, everyone. Now, again, the programs will be very simple. We just need to calculate these numbers using this formula. So you make two loops over n and over k, and then make another loop over j, and calculate this sum. It's something like this one. You should make this for n from 1 to n. You have n here. For k from, it was no more than n, I think, so 1 to n. And then calculate this for j from 1 to k, and then calculate this sum. So it's something like that. It's not exactly, but kind of. I don't want to write the complete code. I wrote too much code today. That's all. Now, if you want to find if you have optimization problem and you want to find the optimal path, you do the same. So you start from the last state of your system, and for each state you know the previous state on this path. So you follow this path from the last state. So last state is when n is the final vertex, and the initial state is when n equal to 0. So you start from the last state and follow these links to the first state. And then you reverse this path and get the optimal path from here to here. Cool. That's all. I forgot something. Yes, you actually can update this. Again, this code works in n square time. And you can easily update it to work it works in n cube time. You can easily update it to work in n square time. You can do this just by calculating this sum first. This sum is not exactly the prefix sum, but it's kind of the prefix sum. So it's, if you look on this array D, what you need to calculate is to calculate the sum of sequences like this. So have n minus j and j. So if you start from some vertex, so this is n, you need to find the sum of cells like this. And these sums also can be calculated like prefix sums. So you can calculate sums like this in two-dimensional array using the same principle as is prefix sums. So you calculate sum like this using this sum plus this element. So you can easily update it to work in n square time. N square time. I believe it's all I plan to discuss today. Yeah. So thank you for joining. Thank you for reading me today. That was fun. So we will see you Sharon next week and discuss more complicated problem, more real life problem of dynamic programming.